In relativistic quantum field theory, of course, you start with Lorentz invariant Lagrangian, but in canonical quantization, you proceed to quantize it with equal time commutation relations, which treat space and time differently. One therefore might expect Lorentz invariants to be destroyed. In this video, at least in the context of real scalar quantum field theory, I'm going to prove that that actually isn't the case. Even after canonical quantization, the theory does in fact remain relativistically causal. So let's get to that. When quantizing relativistic scalar field theory, one starts with this manifestly Lorentz invariant Lagrangian density, which, if taken in isolation, describes a manifestly relativistic classical field theory. However, in quantum field theory, one then quantizes it with these equal time commutation relations, which are often called the canonical commutation relations. And these commutation relations clearly single time out. It treats time differently from the spatial variables such that the commutation relations are in fact equal time. One might expect that this would destroy Lorentz invariance at the level of quantum field theory, but it turns out it doesn't, and we're going to prove that. If you aren't familiar with the process of quantizing a real scalar field, there's a link in the description to my video on that topic. The basic premise of relativistic causality is that no signal can travel faster than the speed of light. In more useful terms, this is the statement that no signal can traverse a space-like separation. In quantum field theory, the relevant consequence of this is that two quantum field operators evaluated at space-like separated points cannot influence each other's effect on the state that the operators are acting on. Such an influence would have to travel faster than the speed of light. This means that when they're acting on the same state in sequence, the order of the operators shouldn't matter as long as they are evaluated at space-like separated points. The commutator of two space-like separated quantum fields should therefore yield 0 when acting on a state. So our effort to prove relativistic causality has left us with a vested interest in evaluating this commutator and exploring how the result behaves for space-like separations. It will turn out that this commutator is actually just a C-number function, and we can prove that it is 0 outside the light cone, i.e. for space-like separations. We therefore will have established that the above statement is true. Let's begin the calculation. The real scalar quantum field is given by this formula, as you may remember from the first video in my quantum field theory lecture series, where as a consequence of the equal time commutation relations, these two operators there satisfy these commutation relations, which I also derived in that video. This phi field, of course, can be split up into two terms, and it turns out it's useful to do that. This is useful because these two operators here each contain only one kind of field operator, so they commute with themselves for all space-time points, meaning these commutators are 0. Therefore, the commutator that we wish to evaluate is just equal to this, so that eliminates some terms, and it also means that we can evaluate these two commutators separately, which is nice because they're commutators of only one-term quantum fields, so we don't have to do any complicated distribution. Additionally, the second commutator follows from the first one trivially, so we really only have to evaluate one commutator of single-term quantum fields, which is really nice. And that first commutator, when we plug in the formulas for the quantum fields, gives us this. In my video on quantizing a free real scalar field, I showed how to evaluate this commutator from the canonical commutation relations, meaning those equal time commutation relations that I showed at the beginning, and I quoted the result up here, right there, and so I'm just going to plug that result in. Inserting that in and doing trivial simplification leaves us with this. We can then take advantage of that delta function to do the k prime integration trivially, and that leaves us with this. And I made a definition here in accordance with the standard notation of this delta plus quantity. This definition here then implies that this delta is by definition equal to that. Now for the other commutator, which, as I said above, trivially follows from the first one, we simply get that it's equal to this. However, this function is itself got a standard notation, and it is I capital delta minus of x minus y. So this commutator overall is equal to I times the sum of these two new functions that we've defined, which itself has another standard notation, and it's just this, where all of the definitions we've made so far, including this one, imply trivially that this new capital delta function is just equal to that, and then we can use Euler's identity to rewrite it like this and simplify it down ultimately to this. This last formula for delta, that one there, tells us something very important about it. It tells us something that we will use later. It tells us that it's an odd function. However, before we move on to the discussion that makes predominant reproductive use of that fact, I have summarized our results so far in this box here. Remember that the original goal is to prove that the field commutator vanishes for spacelike separations. Since that commutator is proportional to this quantity, we must prove that this quantity is zero for all spacelike separations. Because all spacelike separations can be connected by a Lorentz transformation, for example, you can Lorentz transform to make them simultaneous, and because the capital delta function is Lorentz invariant, as we'll prove shortly, all we need to do is prove that it is zero for one spacelike point, and we will immediately know that it is zero for all spacelike points by Lorentz invariance, and therefore that key commutator is, and once we prove that that key commutator is, we will have proved that the whole of relativistic scalar quantum field theory is in fact relativistically causal, so we've reduced down the entire proof to this one little thing. This proves nothing about its value for time-like separations because space-like and time-like separations cannot be connected by a Lorentz transformation. Because it's so important, let's prove that this quantity is in fact Lorentz invariant. Now because this integrand here, excluding all the integration measure there, is purely a function of four-dimensional dot products, the integrand is obviously a simple Lorentz scalar, but we need to prove that this weird integration measure is also Lorentz invariant, and that isn't obvious. I have stated that this kind of integration measure is Lorentz invariant without proof in past videos, but here I will finally prove it for the purposes of proving that this thing is Lorentz invariant. In short, we will see that omega in the denominator combined with this d3k in the numerator is a non-obvious Lorentz invariant combination. Let's start with the fact that d4k is manifestly Lorentz invariant and that this delta function is Lorentz invariant, and the fact that this theta of k0 is also Lorentz invariant because of the form of the theta function and the fact that no Lorentz transformation can connect positive and negative energy values. Therefore, we have that the following quantity, this one here, is obviously Lorentz invariant, and basically we can turn this into something that will tell us that the integration measure we care about is Lorentz invariant. First, let's split off the dk0 integration, and then let's also rewrite the argument of the delta function here. First, we can break up this k squared into k naught squared minus k vector squared, and then we can combine the k vector squared and the m squared to yield an omega squared, so we arrive at this. Theta of k naught restricts k naught to be only non-negative values, so we can rewrite the integral like this, where we used to go from negative infinity to positive infinity, but that theta of k naught made the integral 0 for all those negative values, so we just have 0 to infinity now. We can then factor this difference of squares, and since k naught will never be negative, only the second factor has any capacity to be 0 and trigger the delta function. Therefore, the first factor can be treated as just one extra factor, allowing us to apply this identity here, this common delta function identity. After this, we are free to do the k naught integration. Specifically with that factoring, we have this integral ultimately turning into this one, and then with this identity, we have it turning into that. And then we can easily do that k naught integration to just yield this. It just sets k naught equal to omega, so we get a 2 omega in the denominator. And since this thing was originally Lorentz invariant, we know that this thing must be Lorentz invariant, and that's proportional to the combination we wanted. Or at least it's an integral over something proportional to the thing we wanted. We can easily multiply it by this factor to get it to look exactly like the kind of integral we're interested in, and from that we see that this exact integration measure, the one we're so interested in, is in fact Lorentz invariant. If you combine this with what we've already said about this capital delta function, we can see that it is in fact Lorentz invariant. Therefore, all we need to do, as I described above, is prove that this quantity is 0 for one space-like separation, and we will have proved that real scalar quantum field theory is relativistically causal. Fortunately, this is easy to do. The easiest space-like separation to consider is x and y being simultaneous. So if we rewrite this function like that to make the 0 components explicit, and we set those equal to 0, this function reduces down to that. But then you can see immediately that this must be 0 because the integral is an odd function of k. If that isn't clear to you, I'll explain. Sine is an odd function, its argument is linear in k, and omega is an even function of k, so the integrand is odd. And also this quantity, whose integrand we've just noticed is an odd function, is an integral over the entirety of momentum 3 space. This actually means that that integral has to be 0 because every combination that comes from the positive part of the domain gets cancelled out by an opposite contribution from the negative part of the domain. This argument doesn't work if we can't make the time component 0 because then it isn't necessarily a pure odd function of the 3 integration variables. And with this, we have officially proved that real scalar quantum field theory of the type given by the Lagrangian at the beginning is relativistically causal. So if that was a lot to take in, I'm going to summarize briefly. To prove relativistic causality, we concluded that we needed to show that the commutator of the quantum field with itself evaluated at separate space-time points vanishes outside the light cone, i.e. for spacelike separations. We then calculated the value of that commutator, and it turned out to be the function I capital delta of x minus y. We then proved that it is Lorentz invariant, and then we took advantage of this fact by first proving that it is 0 for the simultaneous subset of points outside the light cone, and then using Lorentz invariance to extend this result to all spacelike separations. So there you go. So now you know how to prove the relativistic causality of real scalar quantum field theory, despite the equal time commutation relations treating time differently than it does space. It's really kind of a cool thing that that doesn't happen to actually cause any problems. But as you saw, and as you now know how to prove, it doesn't. I hope you found this video interesting, educational, and fun. If you did, please give it a thumbs up and consider subscribing.